Good evening, everyone. Hi, my name is Willie Rockford. I am the conference chair, but also the past president of the National Society of Black Physicists. And we are grateful and delighted to have our co-partners, Brookhaven National Laboratories, to share in with this very, very meaningful outreach program that has been spurred by scientists at BNL. And so we're excited to partner with them on this with Girls Inc. and also My Brother's Keeper of New York. And so now I want to turn this over into the hands of our moderator, Dr. Abram Ledbetter, as we move forward in this program.
All right, thank you, Willie. Appreciate it. So I would like to welcome all of you to the National Society of Black Physicists pre-conference, and specifically to the Brookhaven National Laboratories portion in that. I would like to start by introducing one of our esteemed people. His name is David Manning, and he is the director of the Stakeholder Relations Office. David Manning he's developed and implemented government and stakeholder relations programs to help increase support for the lab's programs and priority projects. And he oversees the science education and workforce development programs to fulfill the lab's and the DOE's education and diversity goals. So let me make that simple. He knows about the internships, and he's over that whole body of opportunities that you students like to take part in. So anyway, I'd like to welcome you, David. Please share a few words with our audience.
Abram, thank you, and I'll be very brief. This is very important to us because we've got this tremendous group. We've got partnerships with My Brother's Keeper, with Girls Inc., National Society of Black Physicists, ourselves, BNL, the BNL OEP team who are on, and of course the Brookhaven National Lab facilitates the programming out of the Department of Energy. So what a tremendous group. And these groups now all belong to a tremendous initiative. And Abram, I guess I just have one quick point, and that is there's so many of us here in the system that look a lot like me. And there's going to be tremendous turnover in the next decade. There's going to be an awful lot of opportunity for young people. We need youth. We need diversity of backgrounds. We need diversity of thought. We need diversity of thinking. And what a tremendous opportunity for people who now want to pursue physics and pursue science. I'm a big believer in STEM. I'm also a big believer in STEAM. But all I can say is I'm very proud of the crew that you have here that are supporting you and thrilled to be involved. So thank you, sir.
Thank you. And I appreciate you, David, for what you do and for the inspiration that you bring to the many that get to take part in the programs at Brookhaven. So thank you. Well, we're going to showcase a little bit about Brookhaven National Laboratory because some of you are probably thinking, what is that? So we're going to answer that question, and we're going to do that by showcasing a video. So hold tight and we'll pull that up for you. Oh, wrong video, wrong video.
That's the wrong video?
Yeah.
Okay, you must have another one then. That's what's annoying.
Let's see. It's the very first one. It's the let me I think I can pull this up. Hold on one second. I'm not sure if my audio settings are correct, but let's try this. Okay, actually, I just
You
sent
want
it.
the BNL welcome video?
Yeah, that one. Mhm.
Oh, the one from the beginning. Okay, I
Right,
got it.
right.
All right, 1 second.
The problems that the nation faces are complex. We need science more than ever. Here at Brookhaven National Laboratory, we are looking into little corners of the universe you can only look into at a facility like this. We are trailblazing the future.
The mysteries of matter itself are being solved here at Brookhaven National Lab.
5,000 acres, 300 buildings.
About 3,000 people work here at this facility. It's about a $600 million annual budget.
We have 3,000 to 4,000 people who come in each year to use these facilities to make available for free.
The phenomenal scientists that are here enable us to solve problems that otherwise could not be solved.
We've brought amazing people from around the world. Science is exciting. Brookhaven National Lab is managed for the Department of Energy by Brookhaven Science Associates, a partnership between Stony Brook University and the Battelle Memorial Institute. Ultimately, the science and technology that we do here have impacts on the economy.
What looks like fundamental science is also producing the insights and the ability and applications to do new things for society.
The beauty of this public-private partnership is that it helps us to overcome that area between a new invention and commercialization of that invention.
A lot of fundamental research has to be done before something can actually transition into a product. Here, we can solve some of these initial questions that make or break the future technology.
We're helping other people to really go to the frontiers of science.
We're trying to solve why your cell phone battery dies after a few years, which is new drugs. All these problems that require science and cutting edge science to answer them.
Here at the Relativistic Heavy Ion Collider, it's the only facility like this in the United States and allows us to recreate conditions just like what occurred in the Big Bang. For the good of humanity, we do studies like this to try to understand the way the universe works at that fundamental level. If we understand these quantum materials, we have the potential to revolutionize energy. We have to maintain our scientific leadership, and Brookhaven's proud to be doing that by delivering the world's best facilities and for hosting the experts who are going to be leading in those critical areas for our future.
We have scientists here investigating creation of new materials. It sounds like science fiction, but it's not.
Our job is to help expand countries' energy options. Plants are the future. We're trying to manipulate plants to make more sustainable energy.
A synchronous light source is essentially a very large X-ray machine. To give you a sense of scale, you can fit Yankee Stadium inside this ring. We focused the beam down to about 30 gold atoms. That's a world record. There's no other working microscope that can deliver that.
Batteries are going to be a huge part of the economy moving forward. We're looking for next generation batteries. How can we make them more environmentally friendly and lower cost? The whole world will benefit.
NASA Space Radiation Laboratory is meant to study the effects of radiation so that we can design better shields for astronauts. We also have an isotope production program. We manufacture the radioisotopes that protect people from cancers in the future and can treat the people that have cancers today.
Data-intensive computing is really fundamental. Scientists produce more data that they can analyze. We develop new algorithms and tell them where interesting things are happening. We are helping people to make the discoveries of the future here at Brookhaven National Lab.
We're becoming a technical society. We need a technical workforce. We need to inspire a new generation.
The inclusive environment will allow us to become ever more diverse.
this pipeline of students who are fascinated by science. That's part of the joy of this place. That's part of what we do.
There have been 7 Nobel Prizes for Brookhaven. That passion for discovery is what drives scientists, what makes it fun. It's why we do it. The caliber of the people who work here are the best. They come from across science and support. And every time that this laboratory does something great that has impact, all of us share in that.
We're in business to enable other people's research. They come because we have the greatest machine and the greatest scientists to work with. They can do their research in ways they could not do anywhere else in the world.
In the early days when I was a scientist, it was discovering things that no one else had seen before. That's a real cool feeling, and the confidence that someday it's going to have an impact. Other people are going to build on it, and it's going to help make the world a better place.
Okay, thank you, Menzel. And I'm sorry, I threw you for a loop there. So some of these things are being rearranged on the fly, so I apologize for that. That was my bad. I did want everyone to get a quick glimpse into what we are as a laboratory. If we could, also want to just give a quick highlight from our director, Dune Gibbs. And so we're going to also cue that video. He was not able to join, but he did want to leave a message for especially those who are participating through the My Brother's Keeper and Girls Inc. And so we want to welcome all of you that are participating as high school students, and want to give you a flavor of what you can look forward to in your partnership with Brookhaven National Laboratory, or for that matter, any of the DOE labs. And so Menzel, when you get a chance to pull that up, we'll share Dune's video.
It's a great pleasure for the U.S. Department of Energy's Brookhaven National Laboratory to serve as co-host of the 2021 National Society of Black Physicists Conference. For decades, Nsbp has been a tremendous resource for its members and for the physics community at large. Welcome now to the Nsbp pre-conference BNL Physics Workshop for high school students. This workshop is designed to encourage high school students from Long Island and New York City, from upstate New York and as far away as Baltimore, who are participating in such programs as My Brother's Keeper, Girls Inc., New York State Science, Technology and Entry Program, and others. I hope you'll enjoy what the workshop has to offer, and that it will inspire you to consider careers in physics, or perhaps other fields in science. The strength of the Nsbp is marked not only by its collective influence, but also by its individual members, who proactively shape the culture of science and change the demographics of physics and physicists. As a collective body, Nsbp has played a pivotal role in encouraging the persistence of minority students in physics and related disciplines. Its impact is evident in the growing numbers of students participating in recent years. We hope that these students will consider Brookhaven Lab and the entire DOE complex for internships and eventual employment, and we encourage graduate students and professionals to submit proposals to our user facilities. About us, Brookhaven National Lab delivers discovery science and transformative technology that power and secure the nation's future. Primarily supported by the U.S. Department of Energy's Office of Science, Brookhaven is a multidisciplinary lab with 7 Nobel Prize-winning discoveries and nearly 75 years of pioneering research. The DOE also supports 16 other national labs and would like to share with you the many opportunities that exist across the DOE complex in the hopes of increasing your participation in them. I encourage you also to learn more about Brookhaven, its mission, and its people by watching the video. This is Brookhaven Lab, which can be found at www.bnl.gov/about. Also, be sure to visit the Brookhaven Lab Office of Educational Programs to learn more about opportunities here and to connect with our educational representatives. Welcome to the workshop and have a productive and enjoyable time. Thank you very much.
Thank you. Thank you very much, Menzel. Okay, at this time, I would like to introduce and welcome to the stage Renee Flagler. Renee Flagler is the Executive Director of Girls Inc. of Long Island. Renee is an award-winning writer, adjunct professor, coach, and speaker who is passionate about encouraging women and youth to pursue their passion and purpose. She advocates to youth both in the United States and abroad. Her mission is to empower girls to be strong, smart, and bold, and help them to turn their passion into profits, ultimately to obtain the lifestyle that they truly desire. Renee is the founding board member and former board chair for LEAP, the Literacy Empowerment Action Project Global, an organization with a mission to provide innovative literacy, youth empowerment, programming, and high school scholarships to students in Ghana, Africa. So welcome, Renee. Please, any comments that you would have for our students? Thank you.
Absolutely. Well, thank you for having me, first of all. Thank you so much to Brookhaven National Laboratories, to all the Willies. Abram. I just want to say just a few words to the students. Brookhaven National Laboratory has absolutely been an amazing partner as we at Girls Inc., which you may or may not realize is a national organization, and the Girls Inc. of Long Island, which is where I serve as the executive director, is the local affiliate for Long Island. And nationally and locally, for many years now, we have had very strong initiatives in order to expose girls to opportunities in STEM and foster a love of science, and give them opportunities to engage in science in many ways, interactive, hands-on, amazing experiences. And we've been able to do that through our Brookhaven National Laboratory partners. Now, in addition to being an organization that advocates for girls' rights and gender equity and provides programs for girls to help them become strong, smart, and bold, we love being able to bring them into opportunities that they may not have had an opportunity, have had chances to engage in. And one of those areas is definitely science, and being an organization that also advocates. One of our goals is to make sure that we're able to bridge the gender gap in science fields. So we know, for example, that in the world of physics and very similar to other science fields, women and girls don't make up a very large portion, but the number has been growing as far as the number of women getting involved in areas of science in recent years. Although women of color do remain underrepresented, we want our girls to know and understand that these opportunities are open and available to them. And through partnerships like yours and Brookhaven National Laboratory, that we can bring science to them in a way that is engaging and innovative, and help to foster a love of science very early on, so that when they get to the point where they're making choices for college and careers and things like that, the high school girls, like our high school girls, that they've had experiences, they know what it's all about, and if it's something that's in them, because I think when it comes to a lot of, a focus on passion, and I think a lot of what we like to do is really kind of in us, and it just, we have to come across those opportunities for those loves and those joys and those interests to be triggered. So that's our goal, to make sure that we are giving girls the opportunity to engage and for those interests to be triggered, to foster a love of science, to show them how science meets their life, how relevant it is, how engaged they are in so many different areas of science, every single, especially physics, right? On a daily basis, and how these wonderful studies intersect with their lifestyles, and show them how they can take that, learn more, create career paths, and engage in so many wonderful opportunities. So for girls who are interested in science opportunities, we encourage you to pursue those paths, to reach out to organizations like yours, like Brookhaven National Laboratory, and like Girls Inc., so that we can together help them gain access to these amazing opportunities, because it is so important that the representation of women and girls in these fields continue to grow.
It's absolutely important, and we thank you and we appreciate your partnership, and certainly we do want to ensure that girls and also and especially girls of color who are oftentimes not as privy to these opportunities are able to learn about the great resources and opportunities that laboratories like ours have. And so, thank you.
Absolutely. And
We
thank you.
appreciate you. Thank you.
Thank you.
Thank you, Renee. Okay, at this time, I would like to introduce to the stage my esteemed colleague, Michelle Darienzo from the Office of Educational Programs. She will be sharing some highlights on topics such as radioisotopes in medicine, synchrotron science, and quantum computing. So, Michelle, thank you very much. I think they'll be in for a treat. So I'll let you go ahead and take it away.
Thank you very much. And it was nice to see you, Renee. We miss you very much. Let me just share my screen here before we get started. Hi, I'm Michelle Darienzo. I'm from Brookhaven National Labs Office of Educational Programs. And my computer has frozen. Give me a second. Okay, sorry, I got lost there on trying to share my screen. My computer got very angry, so I'm just going to start over in case you couldn't hear me. So, welcome, thank you. I am Michelle Darienzo. I'm from Brookhaven National Labs Office of Educational Programs. I am here to guide you through a few activities about the science happening at BNL. You should hopefully see on your screen a list of materials that would be really great for this activity. It'll make you have some more fun. You are going to need either 10 coins or one of those like fun size bags of M&Ms or Skittles from your candy bag from over the weekend. You also, if you can find a DVD or CD, it can be just a movie or for music. It doesn't have to be blank or anything like that. Just any old one will do. We won't hurt it. And a flashlight, and you can just use the one on your phone also. That's totally fine. If at any point during the activities you need help, you can type in the chat so that I should be able to see so I can help you out. For any other questions about the topics or about Brookhaven Lab or any of our programs, I'm asking that you please use that Q&A function. So click on Q&A, and that will allow my colleagues Bernadette Uzzi and Ashley Bleidenberg to help me out by going through the questions. And at the end, I'll try to answer as many of those as I can. We'll see how we do with time. If you haven't done so already, please put your first name, your home state, and the organization that shared this event with you. So for any of our younger students, that's going to be something like Girls Inc., My Brother's Keeper, LSAMP, STEM Prep, STEP, NSPE Junior. To give you an idea what we're looking for, if you are joining us from the conference and you are a college student, whether it's undergraduate or graduate, you can put that in as well. So just in the chat, say hello so we know who we're talking to, and just take a moment to grab those materials. So again, 10 coins or M&Ms or Skittles or anything like that, a CD or a DVD, and a light of some kind. So I'm gonna go now because I think everybody hopefully has that. So we're going to start by looking at a group at Brookhaven Lab called MERP. And to understand what they do, we need to start with a little introduction to something called radioactive decay. So to state it simply, that's basically when a nucleus of an atom is unstable, meaning that it really doesn't want to exist, usually because it has too many neutrons. So to solve this problem, the nucleus will release some of this extra mass. In this case, what you see on the screen is in the form of an alpha particle or a helium nucleus. And because it's losing protons, it actually becomes a different element when this happens, because when you have a different number of protons, you're a different element. So the initial nucleus that was unstable is called the parent, and the new smaller one after it loses something is called the daughter. So there are different ways that this could happen. You could lose an alpha particle, like I just showed you. So that would be 2 protons and 2 neutrons. These alpha particles are actually ionizing radiation, which can be harmful to cells inside your body. But because they're actually pretty large on the scale of things when we're talking about atoms, so they can't get through your skin very well. So it's actually really easy to stop them. So it makes them super useful for treating cancer, because if we can get some of these nuclei that are giving off alpha particles next to a tumor, then those alpha particles will kill the cancer cells, but they can't travel very far in your body, so it's not really going to hurt as much else. Another way that this could happen is that it could give off gamma rays to become stable. Now, gamma rays are just light. They are kind of light, but it has lots of energy in a really small wavelength. So that means it can damage cells and it can go through you really well. So you'd think that makes them pretty dangerous, which can be true. But if you use a device that can aim these gamma rays carefully, then you have just created radiation therapy, which is a very successful cancer treatment. So if you only aim at the tumor, that's actually a really good thing because you can destroy cancer cells. Another thing that could happen is the nucleus could give off beta particles, and these are electrons with lots of energy. And these are useful because they can go through your body pretty well, but they're not going to damage your cells as much as an alpha particle or gamma ray would. They're actually much safer. So that makes them perfect for medical imaging because they can go through your body pretty safely, and we can detect the beta emissions to create a picture of what's going on inside your body. So now, why am I giving you an introduction to radiochemistry? Because BNL's Medical Isotope Research and Production, or MERP, group uses particle accelerators and other machines to create these unstable nuclei. And they can emit radiation that will save lives. So this group is probably one of the most disciplinary ones that I've ever met at the lab, because it includes chemists, physicists, engineers, technicians, and they're at all levels of education. Some of them have associate's degrees, some bachelor's degrees, some PhDs, and they all work together to make these medical isotopes safely and efficiently, because there are actually not many places that make them. So it's really important that they're making them as quickly as possible. One of the cool things that they're working on right now is actinium-225. First of all, it's cool because in addition to emitting alpha particles, it also emits an eerie blue light, and you can actually see that on the screen in those little tubes. But more importantly, it's cool because it's being used to treat metastatic prostate cancer. Now, that means that the cancer has spread throughout the body and it's causing immense pain. And that's what you're seeing on the left-hand side. You see all those black dots all over that patient. That patient was given actinium-225 that was attached to something called a biomarker that will guide the actinium to the tumors. And then in the second picture, like, boom, his cancer's pretty much gone. And then, of course, they always do this. They gave him a little bit more just to be sure, and still, the cancer is gone. So in just a couple months, this patient has gone from about to die and in a lot of pain to pretty much back to normal. And that's really amazing. But also, as you can imagine, when you're working with something that can destroy cells, you have to be pretty careful. So because safety is so important at BNL, I also wanted to share with you the last picture that you see in the top right corner. And that is something called a hot cell. These are giant lead-lined boxes that the staff of MERP work inside. They use these robot arms to move things around so that they don't have to be near anything that emits radiation. So it's actually extremely safe to create these isotopes, even though their job is to damage cells. So that's pretty cool. Now, you've been sitting listening to people talking long enough, so let's get you moving. So we're going to do an activity about the decay of these nuclei. So I said before that the parent nuclei become daughter nuclei, so you can imagine that over time you end up with less parent and more daughter. That's actually what you're seeing on the graph on the screen. Now, to be able to refer to how fast this happens, we talk about something called half-life. So that's the time it takes to convert half of the parent nuclei into daughter nuclei. So here's where those coins are going to come in. So grab those 10 coins or M&Ms or Skittles or whatever you have found that has two different sides. We want to represent heads and tails here. And I want you to just grab them and put them all in your hands and shake them up. And then just drop them on the table. Now, if you couldn't find any of these supplies, you can just follow along with me on the screen. Or there is a coin flipper that's free. It's at a website called random.com. And we put a link to that in the chat. Thank you, Ashley. And so you can play along with me, or you can do it at random.com if you don't have coins. So first, just drop them on the table. Then, once you've dropped them, I want you to take a look at what you've got. You may have to spread them out a little to see. And I want you to get rid of the ones that landed heads. So if you see heads, slide those to the side. We don't want those anymore. You want to keep the ones that are tails. So think about it like this, that the heads have become daughter nuclei, so they're useless to us. They're out of the game. And the tails are still parent nuclei, and they can still emit alpha particles or whatever type of radiation you want them to create. So they can play again. So you're going to keep doing this, just dropping coins and getting rid of the heads until you run out of coins. So when you run out of coins, your sample of 10 coins is no longer radioactive because there are no more parent nuclei left to emit radiation. So we want to get to that point. Now, the goal here, so you may want to do this again now that you have a hang of it, is to run through and figure out how many times it took to get down to half of your coins. So when did you get less than 5 left? And how many times of dropping did it take to lose all of them? So take a couple minutes to just shake your coins, drop them, and see how many times you have to drop them to get down to half and how many times you have to drop them to get down to none. So throw that in the chat. So click that chat button and give us a number. So I'll give you a moment to do that. It's the hardest part, sitting here quietly waiting for everyone to throw their coins. Okay, I got 1 from Alexis, 1 flip to 5 coins. Nice. 5 flips to 0. Great. Great. Keep going. I'll take a couple more answers. We'll see if we get the same results. It's always good to get a couple answers before we keep going. And of course, our other panelists are welcome to do this activity too. I don't mind taking answers from you as well. It's okay to act like a kid every once in a while. Okay, Rebecca says 1 flip to get rid of half of them and 4 to get rid of them all. Okay, so that's pretty close. Okay, and Bernadette says 2 flips to 5 coins and 4 for all. So that's actually still pretty close as well. So what you'll notice, and you can keep putting your results in, I'll be watching for it. So what you'll notice is we're going to get similar results here because we're all using coins. So it's the same probability of getting heads or tails either way. So we're all going to get very similar results. We may have variation because it's a very small sample size. So think of it as if we were all working with the same isotope, because each kind of isotope has a different half-life. Good. And Kiro, thank you for sharing. 3 flips to half, 5 for all. Wonderful. So now why does this matter? Why does half-life with coins matter? Well, it's actually really important for medical imaging and treatment. Oh, thank you, Ellis, for sharing. Oh, 2 for half, 6 for all. So good, we're all about the same. So this is important. If you're a radiation technician and you're trying to take images or treat someone, you have to make sure that that radiation is going to still be emitted at the time that you're going to take your picture or treat your cancer. So otherwise, you're not really helping them. So for example, to get a PET scan, medical technicians give a patient radioactive fluorine, which decays pretty quickly. You can actually see that on the graph on your screen. You find that it's basically gone from your body after only 8 hours. But the technicians need at least 10% of that parent nuclei left to get a good image. So they have to optimize the scheduling of patients to allow for the best images from everyone that comes in that day. So actually, it's important not only to the technicians themselves, but to the staff that are running the office and booking the appointment. So it's really important to everybody. Now, how does that work? We get an image from this radioactive fluorine because the particles that it emits as it decays are detected by a machine. It's usually like kind of a cylinder that they slide you into, and you have to stay really still because they want to look at where they pick up those emissions, and then they can figure out, they can actually create an image of the tumor to learn about its size, where it is, things like that. So they actually have to do it, they actually do this in a really clever way, because like if they just put it in your body and it's just everywhere, you're just going to kind of get this big blob for all over. But they need to be able to get that fluorine to the tumor, just the tumor, not everywhere else. So they actually hook it onto sugar molecules to make something called fluorodeoxyglucose. And tumors grow quickly, so they pull a lot of sugar into them, right? They eat a lot of food to grow fast. So that means that the fluorodeoxyglucose will go to the tumors because they suck in the sugar that you eat. That will allow technicians to locate them with the PET scanner instead of using something like surgery. So that's why I wanted to share the MERP group with you, because they're making technologies that are saving lives every day. So now let's jump over to something a little bit different, another group of people that are saving lives, but in a different way. And I'll tell you what I mean by that in a moment. So we're going to talk about one of the big experiments at Brookhaven Lab. It's the National Synchrotron Light Source 2, or NSLS 2. So there was one before, but the 2 is bigger. So it's a bigger, better version of the one that we had before. So here's what it looks like. It's actually really, really big. So it's a circular particle accelerator that is so large that you could fit Yankee Stadium right in the middle if you knocked out like the building that's sitting there. And we'll talk about what I mean by particle accelerator in just a minute. But first, let's get an overview of what this thing can do. So imagine NSLS2 like a giant microscope, and it uses light to study just about anything. So my 3 favorite discoveries that have happened at our light source and its predecessor, so this is some combination of both. The first one that's my favorite is that for the past 2 years, they've been working on looking at the structure of proteins in the virus that causes COVID-19. And this has been important in creating the vaccines that protect us, medications for anyone that has the disease, and we want to make them better because a lot of people are getting very, very sick. So that's been really important over these last few years, trying to get everybody back to normal, and I think we're getting close now. The second one was high school students actually studying the chemical makeup of micrometeorites that they actually collected in a bucket on the roof of their schools. So a whole bunch of teenagers put buckets on their schools and they shined our light source onto things that were in that bucket and found out that they came from space. And they also published a paper about it. So that's pretty fantastic for a high school student. And the last one that I really like, I mean, there are many, but scientists found a hidden painting that had been painted over with another one. And they did it without ever touching it because the light source uses light. So how is that all possible? It's all about X-rays. So the light that comes out of the light source is not like visible light. You can't see it. It's X-rays. So I said before that it was a particle accelerator. To be specific, it's an electron accelerator. So that means it uses electric and magnetic fields to speed up electrons around a ring. So as the electrons move around the ring, and it's supposed to be moving, but it doesn't look like it is on my screen. So I'll try and use my mouse pointer to show you. So their electrons are moving around this ring here, and as they do that, their change in velocity causes them to give off energy in the form of light. In particular, it gives off powerful X-rays. Now this light shoots out straight out of the circle, like straight lines from the circle like this. And we have experimental stations at all those spots where the light shoots out, and those are called beamlines. And you can see a map of our beamlines on the right over here. So what we do is we'll then focus those X-rays onto something we want to learn about and look at the pattern that the X-rays make on the detector. Then we can get a clear picture of what the materials look like at a molecular scale, and we can also find out a lot about their properties from this information as well. So each of the beam lines has different equipment hooked up because they are designed for different types of experiments, but they all start the same way. So this is kind of like a very basic look at what's there. So the light comes out of the ring, and it is what we call polychromatic, which means basically many colors. So the light has many wavelengths. Now for an experiment, what we actually want is just one specific wavelength that matches the size of what we're trying to study. So we need something called a monochromator, which means basically thing that makes one color. So it selects out the wavelength that we want. So that would be here. Once you have that wavelength, then we make sure that the X-rays are focused, and then we shine them on what we'd like to study. Now, of course, for each experiment, there's other stuff in between here that is specific to what that beam line is looking at, but this is kind of the gist of all of them. So now, let's take a moment to just review the different wavelengths of light, because maybe it's been a while since you've seen that. So we talked about gamma rays with our radioisotopes. They're over here on the right. And those are dangerous because they're small and have lots of energy, so they can enter our bodies and cause harm, right? That's what we said earlier. Now we're looking a little bit farther the other way on the spectrum. We're looking at X-rays, which you don't want hitting you all the time, but they're safe enough to be used to take quick pictures of your bones. So that would be like at the doctor or the dentist. Now, two big differences between the X-rays at your doctor's office and the ones at Light Source are the amount of them. There are so many of them at the same time. They're very powerful. And the exposure time. We're creating these powerful X-rays, and usually we're hitting a sample with them for way longer than that quick flash when they press the button at the dentist. So because of this, I once again have to mention safety. So at NSLS2, the experiments that use the most powerful X-rays are actually done inside special lead and concrete rooms called hutches, and those are sealed before the X-rays ever enter them. And once they're sealed, you can't go in, so the samples can only be moved around by robots. So we actually have a whole bunch of robot arms in the different beam lines, which are really cool. And again, because of safety, I'm going to ask you to work with visible light, which is totally harmless. But the idea of this monochromator that picks the wavelength you need is the same for visible light or X-rays. So now you're going to grab your stuff. So grab that flashlight or turn on the light on your phone. And this one's really simple. You just have to shine a light on your DVD. So just shine it right on there, or your CD or whatever. And try to make a rainbow on the wall. If your room is bright like the one that I'm in, you might not be able to see it very well. But if you turn off the light, you should see a rainbow on the wall. Now, you have just shown, if you're able to do that, that your flashlight emits polychromatic light because you can see all of the colors, right? Remember, poly is many, right? Many colors. Now, hopefully it looks something like this, but sometimes it looks more like this, and that's okay. Now, this may seem super simple, right? We just made a little rainbow on our wall. But imagine it like a visible light version of the X-rays coming out of the light source ring. Right now, you're hopefully seeing all of the colors of the rainbow, or the full spectrum. But what we want is just one wavelength. So you would have to find a way to make this rainbow turn into just one color. Now, there are many ways to do this. I've seen lots of students come up with really clever ways to do it over the years. But the one I've had the most success with looks something like this. So you start just how we started. You shine the light on the DVD and make your rainbow. Once you have the rainbow really clearly shining on, say, a piece of paper, you just poke a hole in it. And you actually very simply just block all the other colors. That's it. Make a hole for the one color you want, and all the other ones hit the paper and get stopped. And that's actually a really seems like a really simple thing to do, but it's actually quite difficult. So I would ask you to try it now, but in the interest of time and because it really is very hard to do by yourself, it helps to have a lot of hands. I'm going to leave this as a challenge for you to try later, maybe with your friends or family members. But you're actually, if you could do this, you're making something that works pretty much exactly the same as a monochromator for X-rays. So by spreading out the wavelengths of light, we did it with a DVD. They usually do it with special mirrors that have patterns etched on them. And then having an opening at the exact spot where the wavelength we want is hitting, you can pick just that one. So in the case of X-rays, they typically use things like crystals or, like I said, little like almost like mirrors that have patterns etched on them because they don't react quite the same way as visible light because their wavelength is so different. So that's just a little bit of an introduction to the light source. And now we're going to move on to something a little different. I know it feels like I'm jumping around a lot, but it's because at Brookhaven Lab, we're doing so many different things at the same time. Instead of doing one big thing, I decided to give you little bits of everything. So the last thing is going to use those coins and Skittles or M&Ms or whatever you have again. And it's about a whole group from many different institutions, so not just Brookhaven Lab. It's called the Co-Design Center for Quantum Advantage, or C2QA. And their goal is to improve quantum computers to the point where they can solve big real-world problems. So you can think of the quantum computers of today a bit like prototypes. They definitely work. They can do some really cool things, but once you get to solving those bigger problems, they're still pretty prone to making errors. So what that group wants to do is have many different kinds of scientists, engineers, and technicians all work together to try and make it so that the quantum computers can work really well. So a little bit about what a quantum computer is, because it sort of seems like this mysterious thing. We're going to look at one big difference between the two of them for now, and then there'll be much more that you can learn on your own if you're interested. So first, a big difference between classical computers, that's like the one that you're on right now, and quantum computers, is that classical computers use bits to store information and perform calculations. Now, these bits can either be 0, think of that like the electricity is off, like you flip the switch to off, or 1, where you flip the switch on and there is electricity. So that's all. Electricity or no electricity. That's how all computers work. It's just many switches. Now, because of this setup where bits can either be 0 or 1, classical computers have to run through each of the possible solutions to a problem, one at a time. Now, quantum computers have something called qubits or quantum bits. These can be 0 or 1, just like your classical computer, or they can be sort of anything in between. And you can see by the picture that we represent them a little bit differently. So what do I mean by anything in between? I'm referring to a quantum phenomenon called superposition. And you may have heard of something like this in terms of a cat. You may have heard of the uncertainty principle. Now, this example is from my kid's favorite book, so it's much more friendly than the typical example because it's meant for babies, and that's why I chose it, because it's a little bit nicer. You may be familiar with another example about a cat in the box. Now, this one is a baby looking at a cat in the box. So this baby wants to know if the cat is awake or asleep. In quantum physics, we think of things in terms of probabilities, right? It's all about probability. It's not yes or no. It's how likely is it that this cat is awake or asleep, because we can't see inside. So to us, this cat is like in a superposition of both. And that means that until I open the box, I have to like mathematically consider this cat awake and asleep because I don't know. It's like a 50-50 here. But when I open the box, I make a measurement. I observe the cat. He's definitely one or the other. The only problem is I've now touched the box and I could have woken him up on the way. And that's where that word uncertainty comes from. As soon as you touch something, that could have changed the results. Now, we can also think of it in another way, and I do want to just make sure I am sharing my sound for this, because I'm going to give you as many ways to think about this as you can until you find one that you like. So we're going to think of it in terms of ice cream. So to do that, I want to share with you a video about superposition that was made by a fabulous BNL intern, Nkiru, and I see that Nkiru is here, so thank you so much for making that for us. So I'm just going to ask my team to let me know if it doesn't play or they can't hear it or anything like that. So here we go.
Say I give you this bowl representing a qubit and say randomly dip your spoon in and have a taste. What would you taste? Well, I'm 100% sure you're tasting chocolate ice cream. Same thing with this bowl. 100% you're tasting vanilla. But what about this mixed bowl? What would you taste? You might say chocolate and vanilla, yum! But this is a qubit, so you can only get one flavor. So if you randomly dip your spoon in, what would you taste? Well, since there's more vanilla than chocolate in this bowl, there's a greater chance you'll randomly dip your spoon in and get vanilla. But there's still a possibility of getting chocolate. And that's sort of how a qubit in superposition works. There's a possibility of getting two states, but when you take a random measurement, you only get one.
So even with that great explanation, it is one of my favorite examples of superposition. You may still be confused, and that's okay. That's how we all feel when we start learning about quantum computing. So you'll get there with time and practice. So let's try it with something more physical to kind of help train your brain. So grab 5 coins. So this also works great with the Skittles and M&Ms. So first, just pick up one of them. And what I'd like you to do, and I'll make sure my animation is going here, is to just kind of use your fingers. So put the coin like on edge on the table and like sort of push one hand in the other so that it spins. So just try and get it spinning. You may lose the coin. That also takes practice too. So take a moment to make sure you can spin a coin. And while it is spinning, it's a lot like superposition. The qubit, or coin in this case, has an equal chance of giving us 0, or what we call heads, right? Or 1, and we'll say that's tails. But until we stop it, we have to represent that by some combination of the two, because we really don't know. It could be either or. So that's a lot like a superposition. So once you get a hang of spinning your coin, we're going to start spinning one and then slap your hand down on it. So then you can lift up your hand and take a look. Now that's like observing the qubit. So the superposition collapses, and we're definitely going to get a heads or tails, or a 0 or 1. So when you pick up your hand, just leave that coin how it landed, slide it to the side so that you can remember your results. So then all that's left is to repeat that with the other 4 coins. So when you're done, tell us how many heads you got. So spin it, slap it, put it to the side. Do that for all of them, and how many heads did you get? And you can put that right in the chat. So click that chat button and let us know how many heads you got. Okay, I already see 3 heads, 2 heads, 3 tails, 3 heads out of 4. Great. We'll let a few more people try it out before we keep going. So make your superposition, smash it, then make a measurement and see what you get. Awesome. So it looked like we did get very similar results, and we had an odd number of coins, so it was pretty hard to get a feel for the probability because in theory it should be 50-50 because you have an equal chance of getting heads or tails. So it goes from superposition, where it's some combination of 0 and 1 or heads and tails. And then as soon as you measure it, it's definitely going to be one of those. And then the error that I mentioned in the quantum computers that we have now is like, you can be really sure that you're totally going to get heads from all of your calculations, and that's what you're expecting. But sometimes you get tails. So they're not perfect yet. And that's, again, what C2QA is working on. Now, what's interesting is with the coin, you're basically going to be right in the middle. It's either going to be heads or it's going to be tails. It has to be one of those. And it's a pretty even chance. If you flipped like 100 coins, you'd probably get about 50 of heads and 50 of tails. But with quantum computing, you have a lot more control over these qubits. So you can actually mess with the odds. So you can change the probability of or likelihood that you'll get 0 or 1. So we represent that by a sphere that you can see here. If it's in the middle of the sphere, that's like the coins, right? When the coin is spinning, it would be like in the middle of this sphere because it's got a 50-50 shot of going up to 1 or going down to 0. But you could have a point up here, and the closer you are to the top of the sphere, the more likely it is that your qubit will read out 1. If you're closer to the bottom, the more likely it is that your qubit will end up being a 0. So it's all about probabilities when you're working with quantum computing. So now, why is that important? So the superposition and the other properties of a quantum computer make it possible to speed up solving certain algorithms. So in the example that you see on your screen, which I see is not animating, it's going to show how quantum computing makes a search engine faster. So I'll start that in a second. So for a classical computer, it has to work its way through each possibility one at a time to find the answer. So here you're going to see, and I'll get it started. Oops, I think I got it stuck again. Here we go. So you're going to see that this girl is asking a classical computer, that's when it has the pink background, which is her favorite Pokemon? And this classical computer has to run down the list one at a time and ask, is it Bulbasaur? Is it Ivysaur? Is it Venusaur? And so on, and until it gets to her favorite Pokemon. And you better hope that it's not the last one on the list, or it's going to take forever. Now, there are ways to make that faster with things like parallel computing, and you could make the algorithm a little better than that, but it'll never beat out the quantum computer. So when you see the darker background on that animation there, because of superposition and other properties of quantum computers, or this gives you an ability to look at many possibilities at once. So the computer is just like, OMG, it's Snorlax. And that's it, it's over. And now that's kind of like maybe you're someone who's like less into Pokemon and more into like words and grammar and things like that, right? So let's think of it as asking questions. So I could ask you a series of yes or no questions to get to the answer. I could say, is your birthday November 1st? Is it November 2nd? Is it November 3rd? Or I could just say, hey, when's your birthday? And get the answer right away. So the quantum computer, because of all of the things that make it quantum, it's actually able to get to certain answers much faster than a classical computer. Now, it's not going to replace your laptop, because there are things that a classical computer are better at too. But again, for certain things, a lot of these big scientific problems, and for, like I said, searching and things like that will go much faster with quantum computers. So those things can be faster. So now I think I've left just enough time for questions, so this is great. So I want to thank you very much for playing along with me today, and I am happy to answer any questions if anything popped up through the session and I didn't see it in the chat. Or if you have questions, you can add it in the Q&A or the chat right now. Quantum computing always leads to some questions, so don't be shy. And before we start, I want to kind of preemptively thank our fabulous moderators, Bernadette Bernadette and Ashley. They've been helping out in the chat this whole time. And I do want to let you know that we only have a few minutes for questions because I want to make sure that we have time for our next speaker. So I do apologize if we don't get to everything. So please put any questions you have in the chat or the Q&A. And while you're typing those in, I'll let you know that if you want to do more things like this, go to bnl.gov/education. I see Ashley just put it in the chat. We do all sorts of activities like this all the time, and we also have internships where you can work with a scientist or engineer on our staff. So that would be really great for you. So any questions? I'll give you a moment because I know it takes time to type. I'd be happy to answer them before we move on. All right, and I'm going to hand things back to Abram. Thank you so much.
Michelle, thank you so much. And I appreciate your presentation. That was wonderful. That was awesome. It was also very interactive, and it really helped to drive home the points there. At this time, I would like to take a couple more moments and really vet out any questions that anyone has. I'm going to leave a little room for Q&A. Still waiting actually for someone to show, but in the interim, please do provide any questions that you have. And actually, while we do that, I would like to have a video played in the interim. For those of you that are not familiar with Nsbp, we will show you what we hosted last year was the virtual conference. And so just to give you a feel for what that conference was like, and I think it would be helpful to showcase our video, a promo video from last year. So we'll do that in the interim. And then we have a talk for you, I think, but I'm still waiting for him to join us. So in the interim, could I get that video, Menzel? Sorry to have you jumping back and forth, by the way. Thank you. Thank you.
Can you hear it?
Oh, no, I can't hear.
Hold on. Hold on.
Mm-hmm.
Let's see why you can't hear it this time. Oh, hold on. The headset is off.
I'm the president of the National Society of Black Physicists. I want to.
Okay, you can hear it now?
First time that I attended
We can hear it.
conference.
Thank you.
And actually that experience. Hi everyone, this is Stefan Alexander. I'm the president of the National Society of Black Physicists. I want to invite you to this year's 2020 annual National Society of Black Physicists Conference.
It's one thing in common between you and me. From microscopes of the galaxies, seem like we're getting pulled by gravity. Experiments can prove the theory of relativity. So let's catch the energy, cause we're moving at light speed. Optical illusions, nuclear explosions, out of condensed matter, no matter, only thing matters is this. Where I wanna be, a physicist that look just like me. One thing in common is we are black physicists at Nsbp.
I was shocked. I instantly felt a big sense of community that I wanted to be a part of.
The first time I went to Nsbp conference, I'll just say that I really needed to be there. I really needed to go. And I really needed to talk to, a senior Black person in physics about some of the struggles that I was having when in graduate school. And that conference allowed that to happen.
This is a place where I'll talk to a first-year undergrad about what they need to succeed in college, or a new incoming faculty member about how to apply for grants.
This is an opportunity to learn about what's happening and a broad set of disciplines in physics?
Initially, I didn't know if I wanted to do physics like a PhD, but I met my PhD advisor, Dr. Anthony Johnson. He was looking for students, and that totally changed my career path. So it exposed me to the world.
Yeah, the Nsbp conference is where I actually talked to NASA. They were like, yes, you can do this. And I was like, yeah, you know what? Maybe I can.
This year is critically important since we're in the period of COVID. And so we have to be creative to figure out new ways to be able to stay in touch.
Despite the fact that it is virtual this year, it is not any less important than
Every single year matters. Every year you want to be growing, you want to be learning, and you want to be progressing along your professional path. This is an opportunity for you to foster new mentoring relationships and engage with research and share your research with an incredibly supportive network.
Attending the talks, those ones are really interesting because they're usually something very innovative.
You'll get to be able to hear some of us actually speak, and it'll give you the opportunity to be able to see what people who look like you are doing in the community, and that's extremely important.
The technical talks are geared for all levels. It really is a spectrum across all the topics, and it integrates all different levels of people in a way that many conferences do.
When you come to NSBP meeting, you're coming home. It's going to be a great time. And I look forward to meeting each and every one of you.
All right, thank you, thank you. So in just a moment, we have someone that will be joining us. I'll wait for just a moment to introduce him. He's on his way in. Actually,
Abram,
Menzel,
I'm sorry to interrupt, but the second Michelle Darienzo is Hakeem. I invited him through my link because he couldn't find his, so he's here now.
Okay. Well, so you know what? Thank you, Michelle number one. So I would like to introduce at this time Michelle number two. No, I'm just joking. Let me introduce Hakeem Oluseyi. Oluseyi. I apologize.
It's really close.
I just want to introduce you. Please come to the fore. Thank you very much. Okay, there you are. I see you. Great. All right.
Yes,
awesome.
yes. And you know, I've heard your name over the last year. It's good to finally see your face.
Good to see you too. Good to, I knew who you were. I'm just a little flustered right now, so I apologize.
You know, I did not take the opportunity to you know, cyber stalk you. So this is my first time ever seeing you.
Well,
but I know.
Okay.
Yeah.
I appreciate the opportunity to get to see you here and in our forum here. So thank you. I apologize. We had a couple technical issues there. So I understand that you were here, but you weren't necessarily here. I get it. It's okay.
I was on the wrong link.
Same thing with me too. So that's okay. We'll roll with the punches.
That's right.
Thank you, sir. I appreciate you joining us. I want to just inform everybody of who you are. You're really an awesome guy that everybody should know. Let me say this, Hakeem Oluseyi, he is the president-elect of NSBP. He's an astrophysicist, he's an inventor, a renowned science communicator, global STEM education advocate, and a U.S. military veteran. Hakeem graduated with a BS in physics and mathematics from Tougaloo College and his MS and PhD degrees in physics from Stanford University. He has had professorships at Florida Institute of Technology, MIT, University of California, Berkeley, University of Washington, and the University of Cape Town. And I believe currently at George Mason. Oh, yeah. So,
that's right. Newly at George Mason.
Right.
I'm in my new office where I can't bring in any books yet because they're going to change the carpet over Christmas.
Hey, all right. Well, hey, you know what? I'm sure it'll get decked out soon enough. He also has served as the Space Science Education Manager for the Science Mission Directorate at NASA headquarters and Chief Science Officer for Discovery Science. And as I mentioned, he's currently an affiliated professor of physics and astronomy at George Mason University and president of QuarkStar Incorporated. So welcome and thank you very much for joining us today.
Thank you.
Without further ado, I'm going to let you do you.
Will I be able to share my screen?
Sure thing.
Okay,
Yeah.
and the other thing I want to say is that my title has changed. I'm now a Robinson professor at George Mason University.
Okay.
Yeah. So it's
great.
Thank you, George Mason. And I don't know if you guys know, but the new president is an African-American man who's amazing. His name is Dr. Gregory Washington. Yeah, and he's an engineer by training. He was a dean of engineering, and now he's the president here at George Mason. Amazing man.
I attended George Mason for a little bit, by the way. So
yeah.
So I'm familiar. Yeah.
Wonderful. All right, so I'll get started on the talk. For you students who came out, I just want to let you know that quite often, you don't know what you've gotten yourself into. But if you do decide that what you're learning here today, what you're seeing is for you, you are at the beginning of an amazing story that is going to be your life. And I'm going to share with you my life story and how I became a scientist. Not everything. If you want to know everything, you got to buy the book. But these are some of the major parts. And really, what I want to show you is, many times we have a misunderstanding. You see people like Abram and Katevi Asamagan and Stefan Alexander and all these scientists talking, and you're like, oh man, they're so brilliant. Maybe I could never be them. Well, my first thing I want you to know is we were exactly like you when we were your age, right? None of us start off having everything figured out. And some of us are helped along when our parents are in a particular field. For example, if you would watch the NBA, Kobe Bryant, his father was a professional basketball player. Steph Curry, his father was a professional basketball player. It wasn't an accident that they ended up being professional basketball players. So there are people who have physicists in their lineage, and yeah, they are at an advantage. But that does not mean that those of us who do not have that in our lineage can't achieve it. We absolutely certainly can. And I'm an example of that. So what I'm going to show you here are, it's not a physics talk unless they're a plot, right? So what you see here are these 5 different curves, and each one represents the trajectory of a projectile. Like if you shoot a cannonball off, or you hit a baseball into the air, or you throw something, right? All the same. They all are shot off in the same direction, but they have different starting velocities, right? The slowest one is going 2 units. The fastest is going 10. And, the slower doesn't go to as high of an altitude, and it doesn't go as far in its range, right? The bigger the velocity. But here's the key point. The initial conditions determine the entire trajectory and the final destination 100%. Now, I will show you something. All physics doesn't work that way. I titled my book A Quantum Life. You just heard a little bit about quantum mechanics. And one of the things about quantum mechanics that's different than physics at our realm, and don't get me wrong, quantum mechanics is still happening at our realm. We just don't see it because we're at our realm. But the point is, in quantum mechanics, the initial conditions do not tell you your entire trajectory and destination. What they tell you is the set of possible trajectories and destinations. Some of them have a high probability, and some of them have a very low probability. And I feel like our lives are that way. It can sometimes seem like the family that you're born into, the community that you're born into, predetermines what your life trajectory is going to be and what your final outcome is going to be, right? If your parents do it, you're more likely to do it. So for those of us who come from backgrounds without academic achievement, without a large amount of money, right, then chances are your parents are going to teach you what they know, and they're going to try to teach you even more. But more times than not, we end up being what our parents are. Now, let me tell you about my parents. That's me as a 4-year-old. The young lady with her arm around my shoulder, that's my older sister, Bridget. She is 5.5 years older than me. This picture was taken, shortly after this picture was taken, our parents divorced. And that began our life of insanity. as I'll talk to you about now. But you could look at us and tell we weren't the most economically best off family in New Orleans. Just look at the state of our lawn. But here's the deal. My mother dropped out of school when she was 16. She was pregnant with my older sister, Bridget. My mother's mother also dropped out of school at the age of 16. And my sister, Bridget, dropped out of school at the age of 16, pregnant. My father, that's him right there, he passed away at the end of 2010, but he was born in 1933 in the country in Deep Woods, Mississippi. He's left school at 9 years old. That's the 4th grade. Then he left home at the age of 13 and went to New Orleans. Eventually, he meets my mother after he goes to the Korean War, comes back, meets my mother. They get married. 4 or 5 years later, I'm born. But then they divorce. And we go on a decade-long moving spree. And when I say we, I mean my mother, my sister, and me. From the age of 4 to the age of 13, I move around the country, never living in the same state 2 years in a row. And I lived in some of the toughest neighborhoods in the country. South Central Los Angeles, Houston's 3rd Ward in South Park, New Orleans 9th Ward, New Orleans East, and rural Mississippi. Now, what happened with me is, on the one hand, my mother was an avid reader. She loved to read books. She always had a book in her hand. And she also loved to do Dell crossword puzzles, which had me reading a lot and doing crossword puzzles. So I began to bond with books. I began to love books. Now I was reading children's books, comics books, things that had weird stuff in it, things that were magical, Loch Ness Monster and all that. But when I was with my family, I called that crime school. Why? When I was 4 years old, the year was 1971. And when we left New Orleans, we went to Los Angeles. And my 3 older male first cousins were all members of this new organization called the Crips. It's a gang. And those guys started robbing banks and worse. And they went to prison, 2 of the 3, for a couple of decades. The 2 got out in the early 2000s, one of whom maintained a drug habit while in prison. And when he got out of prison, he started robbing banks again. And he went right back to prison where he remains today and will be for the rest of his life. So that's my starting path. Now, my father, his family had to live by doing farm work, right? So you grow crops and sell them. You have animals, you sell those, or sell their meat. But they also sold alcohol. They did what was called bootlegging, right? It was a crime. When my father got out of the military, he took the crime family to the next level. And he started selling a new product, importing it in New Orleans and growing it in Mississippi. And he's not alive today, but if he was, he'd be tickled to know that his illegal business is now legal in several Western states. But the point is, my father incorporated me into his business from a 9-year-old. And so literally, when no adults were home and people would come to our home to purchase whatever it is they wanted, I would be the one to conduct business. Now, the next year, while I was there in Mississippi for that first year of being reunited with my dad, you know how farm life is. You're doing dangerous stuff even though you're a kid. So I was 9 years old. My cousins that I hung out with were 11. And so, we'd grab shotguns and rifles and go hunting by ourselves, the 3 of us. I'm swinging an axe, chopping wood. We burn our trash. I'm feeding the hogs and all this country stuff. And so to put a long story short, I started playing with fire. And don't do this at home. But I decided to do an experiment. An experiment I decided to do was to hold a flame above the wick of a candle and see how high I could hold it above the tip and still ignite the wick. And I was holding the flame a millimeter or 2 above the wick. But one time, I'm bringing the flame in and it's several inches above the wick and the wick ignites. And I'm like, what happened there? And so I kept trying to reproduce this experiment and I finally did. And I discovered something for the first time that was already known for centuries, but to me, it was completely new. And before the internet was invented, I would go around showing this to people all the time. And everybody's like, oh my God, their minds would be blown. But I'll show it to you here from a little YouTube video. Basically, what happens is when you blow out a candle, the smoke that you see rising up is not smoke. It's actually wax vapor. And that vapor is flammable. And a little ball of flame leaves the source of flame and travels down those wisps of wax vapor and hit the wick and ignite it. Now they're doing a really short jump here, so you don't really get the effect in all its majesty. But this really set me going. Now, the other thing that happened at this time, remember, I'm 10 years old. We've left Mississippi. I'm in New Orleans, the 9th Ward, right? It's a tough neighborhood. And I used to stay inside and read a lot. And we had a set of encyclopedias. And I decided I'm going to read those encyclopedias from A to Z. And I got to E, and I discovered this dude, Albert Einstein, and his theory of relativity. The notion that time is not absolute. It depends on how fast you're moving, which means, and it also depends on gravity, which means that the idea that there's an age of the universe is not really a real thing, right? Because where there is matter, time moves more slowly than where there is not matter. So galaxies are younger than the space between galaxies. But I just got really excited about this, and I decided I'm going to teach myself relativity. And just as I do this, I go into the toughest part of my life up to that point. At the age of 11, we leave New Orleans. My mother sends me away. And in a 16-month period, I live in 9 different households and attend 5 different schools across 3 different states. And these were all tough neighborhoods, right? So I learned what I need to do to protect myself being alone in dangerous circumstances in the hood at a dangerous time. I learned it's better for me to intimidate you before you intimidate me. Now, honestly, that's not the way to live life. But when you're in tough circumstances, as human beings, we're built to survive. So I adopted, the thug persona. So on the one hand, I'm living the gangster life. And on the other hand, I'm being a nerd. So what happens is when I'm a sophomore in high school, my girlfriend gets this computer right here, this very same one. Her mother sent me this picture in 2018, 3 years ago, but she received this for Christmas that year. And, in the country, you didn't date. We did what we call courting. And the way that worked is on a Sunday, the boy would go to his girlfriend's house. They'd sit at opposite ends of the couch for 3 or 4 hours with the family watching them. Then you go home. So I'm like, why am I sitting here with you when I can go learn how to use a computer? So I went and courted the computer, and it had a little booklet that taught the programming language BASIC. So I learned BASIC. Then the next thing that happens is professors show up at my high school and tell us about this thing called science fairs. And little me, not knowing anything about science fairs, when they suggest that we participate, I'm like, okay, I know what I'll do. I'll program all the effects of special relativity. And so I ended up winning first place in the Mississippi State Science Fair in 1985. And the judges say to me, they say, hey, you should become a physicist. You got a big head start. But I had no idea of what being a physicist was, even though I was sort of like interested in it. And coming from where I was coming from, I didn't really see an opportunity in college because I didn't really know what college was. I knew you went to college to be one of 4 things: a doctor, a lawyer, a teacher, or an engineer. I had no idea what an engineer was. A lawyer, that sounded kind of shady to me. A medical doctor, it seemed to me like being president. It's possible, but not necessarily for me. And then being a teacher, I didn't think I wanted to do that either. So I didn't see a place for me. So instead, I joined the U.S. Navy. And I'm in the Navy, and what ends up happening is I get accepted into a program designed for people from rural America that did not get a good education. So in Mississippi, the education level is not as high as in states like where I'm living now in Virginia. All right, that's traditionally. But within the state of Mississippi, when all of Mississippi schools were evaluated 20 years ago, every school in the state was given a grade. Only 4 schools received a failing grade. 2 of the 4 were my middle school and my high school. So I was vastly undereducated. Words like trigonometry, calculus, I never heard those words until I got to the Navy. But luckily for me, first I was able to test into the nuclear program. Then I tested into this program called Boost, which they take you and they give you a year of academic training and then send you to college and bring you back to be an officer. And it was there in the Navy before I got kicked out, because I did get kicked out for having this skin condition that I have, atopic dermatitis. I learned algebra. And if there's one thing I can tell you right now, algebra is not as scary as it sounds. And learning it is the key to all of science, technology, engineering, and math. That is the one. If you get algebraic thinking, then you can do everything that we do. When you think about mathematics, everybody thinks numbers. But to the point, all the number math you need to know on most days is how to add and multiply the single digits. That sounds crazy, right? But it's absolutely true. But here's the difference. If I were to ask you, what is 2 alligators plus 3 alligators? You'd probably say 5 alligators. But if I was to ask you, what is 2x squared y cubed z plus 3x squared y cubed z? You'd probably go, huh? But it's the exact same problem, right? It's just that the way it sounds, we've been trained to go, the second we hear the word X or something like that. But it's the exact same thing. Whatever comes after the number is the kind of thing, like an alligator, a refrigerator, a door, a galaxy, right? 2 galaxies plus 3 galaxies, 5 galaxies. 2y plus 3y, 5y. 2 coffee cups plus 3 coffee cups, 5 coffee cups. Same thing, right? So anyway, I learned algebra. I get out of college. I get out of the Navy. I'm an aimless guy out on the street, and my friends convinced me to go to college. There I am in the Navy, and I go to Tougaloo College. But when I get there, it's serious. It's serious academics. I haven't had serious academics in my life yet, right? I attended my high school, which wasn't the top academic school. And the way we're taught in the military is very different than the way it's done in college. So I felt like I wasn't ready for college. And ultimately, I dropped out of college. And I took the job I could get. Now, I kind of fast forwarded in the story. The other part is that I went back into a life of crime, right? My father had a business, and now I had a business, and I was in business with my father. And at this time, though, things were changing. It was a new business, and it was a very dangerous business. And I found myself looking down the stupid end of too many gun barrels. So I decided I was going to change my life, but I didn't decide fast enough. And the other thing about me was my first 2 summers in college, I was homeless. Not living on the street homeless, couch surfing homeless. And my second summer, I ended up getting a phone call from the University of Georgia asking me for my social security number so that they can pay me when I get there for their summer research program. The thing was, I did not apply to a summer research program. So I went to our science building and I ran into this man right here. That's Professor Richard McGinnis. He was my chemistry professor. I said, Professor McGinnis, do you know anything about this? And he replied, oh, they accepted you. It turns out they had called Tougaloo and asked for him to make recommendations for someone, and he recommended me. And I said to him, I said, you know what, Professor McGinnis, thank you, but it really doesn't matter because I don't have any money to get to Athens, Georgia, and they weren't paying my way. So Professor McGinnis went into his pocket and purchased my tickets to get to Athens, Georgia. And when I got there, I ran into this guy. I worked for him that summer, did the very first real scientific research of my life. His name is Dr. Michael Duncan. Now, what he did was the following. After he told me what my job would be in his lab, he said, you know, we researchers keep weird hours, so you're going to need to be able to have access. So here's a key to the building, here's a key to the lab, and here's a key to my office. I darn near fainted because being the dude I was, growing up in the hoods I grew up in, I may have been given many things many times, but never was I trusted, right? No one gave me trust. And this dude gave me trust day one. And I was like, what? What the, you know, I couldn't believe it when he handed me the keys to the building. So of course, I robbed them blind that summer. Just kidding, I did no such thing. But what happened is at the end of the summer, they told me, they said, Akeem, you're great at this research thing, man. You should do it. And I thought to myself, wait a minute, you're judging me on the merit of my work rather than some arbitrary whateverness? And I'm like, this research is a thing for me. And what did I do? I went right back to Tougaloo College, got right back involved in a life of crime, went really deep and dropped out. And I found myself at a point where I thought I'm not going to live very long. So I realized I needed to change things up. So I temporarily left the life of crime and I got a job, the job I could get, which was as a janitor at a nearby hotel, the Ramada Renaissance Hotel. And what ended up happening is I was making $4 an hour. I was only getting like 20, 25 hours a week. Do the math yourself. And, taxes get taken out. And I barely had enough money to pay my rent every month. So the way I would eat is that when people would order room service, they would put their trays outside their door, right? And so when I got to work, I would walk through the halls and eat people's leftovers from off of their trays. And then my big break occurred. And that was the bellhop got fired, one of the bellhops. So I thought, if I get the bellhop job, I can make $100 in tips in a day. Whereas I was barely making $100 a week. And they looked at me and decided, you're not front door material. So I thought to myself, I can't go from janitor to bellhop. I'm going back to college. So I re-enrolled at Tougaloo College. And this woman showed up on campus with a guy named Aya Kutbach, who is now a physics professor at Morehouse. She right now today is a scientist in San Antonio, Texas, and Claude Poo. And they told us that they had just started a conference called the National Conference of Black Physics Students, and they want to invite us there and tell us what a career in physics is. And this was a huge break in life for me, just like going to the Navy and learning algebra was, just like going to the University of Georgia and doing research for the first time was. And here's what I learned what being a physicist is. And that there's a thing called graduate school and how you get in, and that you that you choose research in these particular ways. You choose advisors in these particular ways. And basically gave me a roadmap. And I miraculously got admitted to Stanford University. And I worked for this gentleman right here, the late, great Arthur Bertram Cuthbert Walker II. His father immigrated to the U.S. from the Caribbean, and his name was Arthur Bertram Cuthbert Dalrymple Walker. But when they immigrated, they dropped the D. So instead of being ABCD Walker, he was ABC Walker. And this guy was a gentleman's gentleman and a scholar's scholar. And just being around him every day throughout the 90s taught me a different way of being, right? I was, thug lifed out when I showed up at Stanford, but this man showed me a different way of being, but he also taught me how to be a rigorous scientist. And he was also there for me when I needed him. I had tough times when I first got to Stanford, and not all of it was fair. And he protected me, he defended me, and ultimately I was successful. Now, what did we do? Oh, that's me in graduate school in the 90s in our office, doing space research, studying the sun. And if you've ever seen pictures like this with the plasma loops all over the sun, we were the first to do that. Now, I was a junior person. Art Walker was the leader. I'm not saying I did it, right? Everything we do, mostly, we do it in teams. But here's our original data. This is now the standard in the field for imaging the sun. And it's also used in making computer chips. And immediately after graduate school, so I got my PhD using this data. Here we are at the 94 rocket launch. If anybody watches Ancient Aliens, the gentleman there in the white blazer, that's Richard Hoover. He's always on Ancient Aliens. What happens is, here's our spacecraft. It was called the Multispectral Solar Telescope Array. Every hole you see here goes to a different telescope. I have to go grab a power cord. I'll be right back. I'm so sorry. I'm still here, y'all. I'll be right there. All right. I didn't want my laptop to fall. So every hole that you see there goes to a different telescope. We would fly 16 to 22 telescopes at a time, each one imaging the sun's atmosphere at a different wavelength and at a different temperature. And so the point is, here's the point. I was able to get by and become a physicist based on hope, hustle, and help. And without help, I would not have made it very far at all. So those of you who are students who are observing this or want to be students recognize that now that you have connected with BNL and an NSBP, you now have help, right? You can look at my social media. You can contact me anytime, and I can speak for the rest of the members of the NSBP. There's so many of us that are enthusiastic about helping you. But here's the other thing. Because I know that I would have gotten nowhere fast if people had not helped me, and education was the key for me, it was immediately a responsibility to help others. And one of the joys of my career has been working in Africa. So here I am in 2002, I got my hand broken playing basketball. Here I am again in 2003 in Zambia, and look at the lady behind me with the ball under her arm, teacher. Here we are again in 2006. She worked in Nairobi as an accountant, and she participated in this outreach program called Cosmos Education. And it was at this particular event here in 2006. The guy in the yellow shirt, by the way, is Dr. Alphonse Sterling. He's a African-American NASA scientist, and we studied solar eclipses together. And there's a video, a documentary made by Dr. Jarita Holbrook about the two of us in our work. But anyway, Susan announced to me that she wanted to go into astronomy, and I took her under my wing, and she's now become an international superstar. I even introduced her to her husband, Chu, and they have this thing called the Traveling Telescope, and they're both amazing people. This young lady here in green, this is Dr. Samaya Fareed. She came and worked for me. We were there in Ghana getting her thesis data. She worked for me the summer of 2002. And the funny thing is, we should tease each other over who was more country. Not saying you're more country than me, but I'm more country than you. So when I told her, I'm like, she's from Southern Alabama, I'm from Southern Mississippi. So I say to her, oh, you're more country than me? Well, my high school graduating class was 70 people. And she was like, oh yeah? Well, my high school graduating class was 20 people. She wins. But anyway, she had worked for me in the summer of 2002, and she had the it factor. You can do this, Samaya. And so coincidentally, I'm in Alabama 3 years later, and I run into her in a parking lot randomly. And I'm like, Samaya, what are you doing now? She had graduated a year earlier. And I'm expecting to hear something incredible because she's incredible. And it wasn't incredible. And I was like, how did this come about? And she told me, and I said, well, you know what, Samaya, we need to get you back in school and get you your graduate degree because you're an awesome, talented person. This can't stand. And there we were in Ghana getting her PhD, getting her master's thesis data. Well, today she is Dr. Samaya Fareed at Yale. And the woman sitting next to her, that's Jessica Williamson, and she's been a Boeing engineer ever since that. She was an undergraduate at the time. And so the point is, not only you might be in a struggle like I was, but you can also help people. And that's what I go about doing every day. So here we got a grant. The NSBP got a grant from the Kellogg Foundation led by Dr. Charles Magruder. And as of 2008, they had only produced 3 Black PhDs in astronomy in their entire history, even though they're one of the top astronomical countries in the world, going all the way back to the 19th century. But they weren't producing Black astronomers. So with this grant from the Kellogg Foundation, we went over there knowing that the problem is not one of academics, right? There's more elements to this, right? And not only did all of our students pass to stay and get their graduate degrees, the faculty at University of Cape Town reported to us that they all passed in the top 20%. So now South African astronomy has been completely transformed. And here I am, I'm there for in Cape Flats for the United Nations doing that. Here I am in Algeria for the Department of State for the United States because, we help other nations to develop their space programs and their science education programs. And here I am right before the pandemic in 2019 in Indonesia. And, helping each other is our human superpower, right? And so together we can do anything. And so when you do help people, you never know where it's going to end up, right? There are people who helped me young in my career, and they can call me every day, and I'm going to show up to help them out. That's how much I appreciate them at zero charge, right? Even though normally I charge people when I show up. And so you don't know where it ends up. So I want to leave you with this video because this one was something that happened to me that was unexpected. I did this thing for PBS every year called American Graduate Day, and it's about mentoring. So they surprised me in 2018 with this.
Command issued and liftoff. Mark Vande Hei, Alexander Mazurkin, and Joe Acaba lifting off and now on their way to the International Space Station.
I'm NASA astronaut Mark Vande Hei on the International Space Station orbiting 250 miles above our planet. And it's great to be a part of American Graduate Day. I've been
Wait. Uh-oh, sorry about that. My baby boy came in.
I'm NASA astronaut Mark Vande Hei on the International Space Station orbiting 250 miles above our planet. And it's great to be a part of American Graduate Day. I've been fortunate to have had great mentors in my life during both my Army and academic careers. In fact, while Stanford University studying for a master's in applied physics, one of the people who helped me along the way was Dr. Hakeem Olusay. Hello, Hakeem. Houston Station on Space to Ground 3. NASA is a wondrous blend of science, engineering, technology, with mentors at every step of the way. So become a mentor, just like Hakeem was for me.
The Spider-Man.
Whoa, help me.
All right. So I'm going to stop there. Thank you all very much. And, you know, I got an amazing book out. Check it out. Is there any questions? Are there any questions?
Well, first, I want to just say thank you, Hakeem. That was amazing. As always, your presentation is always very inspirational, and mentorship is worth doing backflips over. So I get where he's coming from, and you know, whether you're in space, in zero gravity, or on the ground, you know, it's definitely mentorship is really critically important, and that's what. The Society of the National Society of Black Physicists is largely about. You know, continue to encourage the persistence of Black physics students and brown physics students. And so, you know, you have definitely demonstrated that legacy, and your story is quite impressive. First time I heard it, I was thinking, when is the movie coming out?
So I'll tell you, it's funny. So I did get a movie deal with Chadwick Boseman and
awesome.
Working Title with Universal as a studio, but you know, they sign you for what's called an option for 18 months. And if the movie doesn't go in production in 18 months, then they got to renew the option and pay you a little fee again. And so my first option ended in March, and in May, Universal informed me that they're not going to go forward because of Chad's death. So we went back out, and just last week I got a new offer, and now I'm in business with Oprah Winfrey.
Whoa.
Yeah. Yeah.
Oh,
and De Niro, Tribeca company. Yeah. So I just got the offer last week, and I'm like, it's a go.
Congratulations. That's
Thank
amazing.
You.
Well, that actually answers one of the questions. We got a question that says, what is next for you, Dr. Oluseyi? So do you want to elaborate on that? Anything else?
Oh, yeah. So the first thing is, you know, it is an honor and a privilege to serve as president of the National Society of Black Physicists. And, you know, the one thing I want to do is what's already being done is, you know, helping our membership to thrive, right? That's, you know, the professionals. You know, I think that sometimes when we're talking about education, we always focus on the kids, but, you know, it's sort of like in the airplane, they say you got to put your face mask on first. And, you know, we need support and mentoring throughout our careers. So what I want to do is really help to promote the careers of the professional physicists. But also I'm starting my next book, my second book. When I got a deal, it was a 2-book deal. And so this one will be a science book. And if you're into watching television at all, turn on Netflix. I'm in a new show called Baking Impossible. It's always in the top 10 in Netflix these days. I serve as an engineering judge. What they do is they partner a baker and an engineer, and they build cakes that have to like survive challenges. So, you know, build a 4-foot cake that sails through this thing, and, you know, so yeah, and I've now started I've been out of the classroom since 2014. I will be teaching 2 courses next semester at George Mason University, and hope to get my research group here started.
Oh, awesome. That's incredible. Any other questions? Please feel free to use the chat or, well, I guess that's really it because you can't unmute. So, okay, so another one here from Ellis. What advice would you give to people that want to do astronomy for a living?
Math and computation are going to be your foundations, right? Understand that a lot of people go about choosing their majors in college in the following way. They say, okay, what do I like that does not have math and I can make money at it, right? So with anything, you're very capable of doing math, but, with anything, it's a number of times you do it. And the problem with our academic system, our education system, is that they convince you that math is all about numbers until you're in high school. And then they're like, oh, here's this weird thing called algebra, right? And so they should institute algebraic thinking at the very beginning instead. So what are you doing, kiddo? So, get up on your mathematics, and definitely computing is one of the skills. And of course, the most important thing you can do is find someone who's doing what it is you wish to do, or at least more farther along in it than you are, and spend time with them and sort of become an apprentice to that person.
So by the way, so we have in our audience, we do have a number of high school students, as we mentioned, but then there's college students as well. So for some of them, I guess maybe looking for internships where they can.
Absolutely. You should try. The research is such a weird thing. It's not natural for a lot of people. So the sooner you can get involved in research, the better. You're better off. So if you want to be a researcher, get involved in research as quickly as you can, because it's not and I'll give you an advice, make a plot. That's how you know you've actually done some work. No matter if you're doing instrumentation or theory or data analysis, whenever you do work, it results in a plot. So when you join a research group, make sure you make a new plot every week.
That's great. That's great. Any other questions? So by the way, while I'm looking for a couple of more questions, and we'll take maybe one more, but I'll just kind of insert before that, because I know that we'll have to wrap up and then let Willie take over. But I think it's good that you showed the broken arm, to show that, hey, we actually have other things that make up who we are. We play basketball.
Absolutely.
Or in my case, I like to freestyle and rap.
You too?
There you go. So, I like jazz. I play several instruments.
You too?
Absolutely, absolutely. So being a scientist doesn't limit you from being a human.
A full
there's a perception issue a full human. Sometimes there's a perception issue that that you have to be a certain way,
right?
And so I think that's important to demystify.
I agree. Yeah.
All
right. Well, thank you all so much for having me. It was an honor to be able to speak to you today. And just know that you got this, those of you. And if you do join this life, it is full of benefits that you can't even imagine beyond, a paycheck, and you do great work. Stop Absolutely. It. For example, I've been to 41 countries, and guess how many of those trips I paid for? 0, right? Life of a scientist. Okay. Right. Stop it. All right. So thank you all very much. I got to put somebody to bed right now.
Hey, we hear you. All right. Thank you again, Dr. Olusegun.
All right. Y'all take care.
You too.
All right.
All right. I just want to thank everybody who's participated, everyone that's presented. Appreciate your time. Thank you for the questions, students. Hope you enjoyed it. And I want to pass this back over to Dr. Willie Rockwood. And by the way, you look real good, sir.
Man, Hakeem's presentation always get me so hyped up, man, and excited. I was like, wow. I mean, and I knew him all along. His journey and things like that. And But every time I hear him, I just get more and more excited about.
I do too. That's
physics,
amazing.
about everything. Yeah.
Yeah, yeah.
Well, we are ever so grateful and thankful for this partnership between BNL and Nsbp, and also with Girls Inc. and My Brother's Keeper, and oh man, it's the other organization that's in Baltimore. It slipped my mind. University of Maryland,
Baltimore County,
Baltimore campus.
Yeah.
They're doing their outreach too, and we're just so ever grateful for this collective partnership of sharing, of coming together, sharing the various opportunities and things that to push the next generation towards having careers in STEM, and especially in science and physics and astronomy and things of that nature, and to know that it's cool. It is cool, and it's cool to be involved in those things. But those, especially our students who are in high school and middle school and things of that nature, your mathematics is the key. Okay, mathematics is the language of science. If you're going to do anything in science, engineering, anything, you got to get that math down. And it's not that hard. It is not hard. It's just the two more universal languages. The two universal languages. It means everything in the world that are common is music and mathematics. And most of the time in our culture, we can do both. Okay, if you can hold a beat, you can count, and you can do math, and it's not as hard. You just got to work at it a little bit. It's going to take a little time. It's not going to always come easy, but you can do it with no problem. So again, thank you all. We had a great time. I know we had a long day. I had a long day, but we're ever so thankful for this informational session. I love the little coin example with the radioactive decay. I mean, it tells you how we as scientists and engineers and so forth, we get creative in sharing what we've learned, and that there's a lot more things to be explored, and that we need the next generation of scientists and engineers to get involved from all communities, and especially those of underrepresented minorities, those who look like me, and Abram, and we just not that many of us going into that field, and we're definitely more capable of doing so. But nevertheless, don't want to hold an hour. It's good to see Menzel, my good friend. Glad to see you.
And I do want to give a special thanks to Menzel because she has really filled in, just kind of coming back, and she's filled right back in. And then especially with me throwing a lot of weird things out there, but she's catching them all. So I appreciate you. Thank you, Menzel. I appreciate that. Thank you. Yeah, and once again, thank you for everybody who's participated, who's helped. And thank you, Dr. Walker, and for the NSBP for your partnership. We appreciate you, and thank you so much for allowing us to have this time to share. So thank you.
Okay. And David, glad to see you back too. David, any final comments you'd like to have?
It was such a great night. I really pleased that you included us all, and again, special wishes to Menzel. Menzel, it's wonderful to see you. It's great to see the family together, and it's great to be part of this. So Willie, thank you. Abram, well done. And what a treat. That was a kid. All right. Thank you. My sincere thanks.
Well, we hope to see everyone for the conference. We're starting up tomorrow. It's going to be a long day, but we hope to see you in and out and enjoy. And remember, y'all, that we have the big science hour, this is our inaugural event. This is our first time doing this in any of our conferences, and we're doing the first one with BNL. So we're looking forward to hearing the big science at BNL, which is in this year is the electron ion collider. So forward to that tomorrow, and many other things in the conference.
Indeed.
Again, everyone have a great night, and we'll see you soon. Goodbye.
Everybody take care. Bye-bye.